Hey everybody, welcome back to day 3 of chapter 15, Equilibrium Chemistry. So before we get rolling today, I just want to let you know that this is a large lesson, probably the biggest one of the chapter, and for sure one of the biggest ones we've done online this year. It's going to take us, I bet, 35-40 minutes to get through this one. So if you're looking for a quick little lesson here and you only have 20 minutes, don't bother. Set some more time aside or plan on doing it in 2 chunks, because this one there's just a lot of content to cover today, and we're learning all the really critical skills that you need to be able to be successful in this chapter. It's kind of like in redox when you learned how to balance redox reactions using the half reaction method, and then we just used it forever throughout the unit. Same kind of idea here with ice tables and equilibrium constants. So big topic, really important. Today's Thursday, so at the end of this lesson, I'm going to give you your assignment that you can start working on. You won't get any new content tomorrow because you need a bunch of time to practice this and work on the optional assignments and the assignment that you're going to hand in to me as well. Okay. So let's rock and roll. So in your study guide, you are on page 309. And you need a graphing calculator. Today's the day we start to use the graphing feature on your calculator. I put a link in here if you don't have your TI-84. I think you can get an emulator or a facsimile of one online that you could use, but hopefully you've got one at home, or you can borrow one from a friend who has one that's not using it this semester. Just wipe it down to make sure it is safe to use. Okay, here we go. So we're going to learn about the equilibrium constant today. This is a mathematical constant. So what have we got in here that you need to know? So the equilibrium constant, written as Kc, sometimes you'll see it as Keq, okay, is a constant value over a range of amount concentrations for a reaction. So it can be written out as a law or an equilibrium law, and this is what the law looks like, and I think this is what you have to do in your notes as well. So if you had a chemical reaction with lowercase a moles of chemical A, B moles of chemical B, C moles of chemical C, and D moles of chemical D, this is what the equilibrium law expression would look like. The equilibrium constant is equal to chemical C to the exponent of its number of moles, chemical D to the exponent of its moles, and what this means is products on top and reactants on the bottom. So that's your first key idea. When you're writing out these equilibrium law expressions, you always put the products on top, reactants on the bottom. Now, this law is kind of weird to look at, so let's use a slightly more realistic example. Here's a chemical reaction. 2 moles of A reacts with 1 mole of B to make A2B. Write the equilibrium law expression. Okay, so for the expression, you put products on top. So it's the concentration of A2B over reactants on the bottom. A times A, because we have 2 moles of A and 1 mole of B. Now we can combine these. A times A is A squared. So that's where those exponents come from. So if we had a chemical reaction with 3 moles of KNO3 in the equilibrium expression, we would write concentration of KNO3 cubed. So that's where these come from. They represent the number of moles, 2 moles squared, 3 moles cubed. We don't go any higher than that. Okay, so, and again, it's a ratio of products to reactants, and we only include concentrations. It says to omit solids and liquids from the calculation. So, for example, if this was a solid, this would be gone, and you would just have a 1 there. Now you might be thinking, why? Why don't we include solids and liquids? Well, it says to only include concentrations, and concentrations are moles of chemical dissolved in liter of solvent or liter of gas. So aqueous have a concentration and gases have a concentration, but a solid or a liquid does not. When you have a block of solid metal, there's no concentration to it. It's just a mass of metal. Or if you have a container of a pure liquid, there's no concentration. It's not dissolved in anything. So that's the reason why we only use aqueous and we only use gas in our equilibrium expressions, because this is an expression of the ratio of concentrations of products to reactants. Lots of talking, lots of theory. Okay, let's practice it. So, excuse me, in your notes, you have this chemical equation and you're asked to write out the equilibrium expression. Kc is concentration of NO2, and there are 2 moles, so it's squared. There's our products over reactants, concentration of NO squared. And I should be saying equilibrium concentrations, because this is the equilibrium constant and it uses equilibrium concentrations. And equilibrium concentration of O2 to the power of 1, or we don't even need to put the 1 there. Just the same reason we don't bother putting the 1 there. Okay, that's the equilibrium expression. Now we want to actually calculate this mathematical constant. So Kc or Keq, same thing. All right, so now all we do is we plug in the equilibrium concentrations. So NO2 is 0.8. 0.8 squared. If you want, you can put brackets around it. And on the bottom, I'm going to put brackets around this whole thing. We have concentration of NO, which is 0.3 squared, times concentration of O2, 0.5, not squared. Okay, make sure you have brackets around the entire denominator. That is important, okay, for order of operations. Plug it into your calculator and you get 14.2, and I always like to put it over 1. Why do I do that? It shows me the ratio of products to reactants. So in this chemical reaction at equilibrium, we have a lot more product than we do reactant, or we would say that it favors products. Okay, the chemical reaction ends up on the product side with more product, less reactant. Okay, let's try one more. Write out the equilibrium expression. Kc or Keq is the equilibrium concentration of Mg2 plus over equilibrium concentration of copper 2 plus. Now notice this is a solid and this is a solid, so they are not concentrations. They're not included in the equilibrium constant because they don't have a concentration. Okay, this one's easy. Nothing squared, nothing cubed. We substitute them in. 4.0 is the equilibrium concentration of Mg2 plus and 2.0, which is 2 over 1. So this reaction also favors products because we get 2 product for every 1 reactant, and we can see that simple ratio there. 2 product for every 1 reactant favors products. Okay, I'm not even going to do this one. It's the same pattern as above. We're excluding the liquids. I'm just going to clean that up a bit. So we're excluding the liquid, excluding the solid, and it's going to look just like the one above. Okay, so hopefully you have a good grasp of writing out the equilibrium expression and calculating the equilibrium constant using equilibrium concentrations. Okay, a little more theory for you. So I've already said that Kc is a ratio of products to reactants. Okay, you can use this to determine the relative position of a reaction at equilibrium. So as I've said, always write it over 1. So when you calculate the value, you just get a single number, turn it into a ratio, and then beside it put P over R. And then you can tell me very quickly what's favored, products or reactants. So here's another example. Kc is 0.0355. Does this one have more reactants or more products at equilibrium? Well, let's write it over 1. let's put our products over reactants. So we have 0.0355 products for every 1 reactant. So that means that it favors reactants. There's a larger amount of reactant than product at equilibrium. Okay. What is the equilibrium constant for this reaction? Kc is products over reactants. We have 5 moles of product over 5 moles of reactant. Interesting. This one works out to be a 1-to-1 ratio. So does it favor reactants or products at equilibrium? Well, that's a trick question. Neither. It's equal. Very unusual to have a product that sits at 50% reactant, 50% product. But that's this example, and you can see it there. Equilibrium concentrations are equal, 50-50. Okay, so some statements that we need to understand and be able to make. When the equilibrium constant is greater than 1, so for example, let's say it was 3.6 over 1, we say that the reaction is greater than 50% to the product side, and products are favored. Makes sense? Sure it does. Okay. What about when the reaction is less than 1? So that would be this example. If it is less than 1, then we say the reaction moves forward less than 50% or less than halfway, and it's favoring the reactants. So it's stuck on the reactants side. And then the two extreme ends of the spectrum, if Kc is greater than 100, so let's say that the Kc was 480 products to reactants. That is almost all product. So we say it's greater than 99% product, and we call it a spontaneous reaction, which means you can assume that it pretty much goes all the way forward, greater than 99%, and you could use a single-headed arrow. What if Kc is less than 1/100th? So Kc is 0.00063. So in this example, we have almost no product, all reactant. We say that it is less than 1% product, and we call those reactions non-spontaneous. EOUS. Okay, so hopefully that makes sense for you as well. How's everybody doing? Good? Sunny day today. Yay. I'm going to take a lunch break after recording this lesson and go sit outside and get some fresh air. I don't know if you noticed my tan, but I have been every evening outside and the weekends outside. I have a big yard. I'm digging around, putzing around. I got a new puppy I'm trying to train, and that dog has to go pee every hour. I don't take him outside. I'm cleaning up pee on the kitchen floor, and that's no fun. So got to stay on top of that. Having a puppy is like having another baby. My youngest daughter is 20, just turned 21 a few days ago. So it's been over 20 years since we've had a baby in the house. So I kind of forgot. Crying at night, getting up early in the morning, but no diapers. I just have to remember to take him outside every hour on the hour, or it's cleanup time. Okay. I digress. Okay, so equilibrium constant is a constant value at a given temperature. So you'll notice that they always say Kc is this value at this temperature. And this is a really important little concept. It only varies with changes in temperature. Okay, so if you heat a reaction up, its Kc value changes. If you cool it down, its Kc value changes. Here's the weird part. The following do not affect the equilibrium constant. This is hard to believe, but if you change the concentration, it does not change the equilibrium constant. Your final ratio ends up being the same. If you add a catalyst, it doesn't change it. If you vary the time for the reaction, it does not change it. All three of those do not affect the final ratio of products to reactants. That is a constant value for any given reaction, and it does not change, only temperature does. Okay, some students think that if you have a really large Kc value, the reaction happens fast. Okay, no, not necessarily. All we know is that it favors products if Kc is large. It's not an indication of rate. Okay, do I have the word rate in there? Yes, I do. It does not tell you the rate of a reaction. It only tells you the equilibrium position. Phew, okay. So that's all the background information and the theory. So what we're going to do in the second half of the lesson is, and this is the big part, you guys are going to learn how to use equilibrium constants with ice tables. And we're going to be doing this throughout the chapter. So it's a big skill. Get your graphing calculators ready. Here we go. Okay, now you know how to determine the equilibrium law, calculate K, and set up an ice table. We can do the more complex equilibrium questions. So here's our equilibrium reaction. They're giving us the equilibrium constant, which is the same as 0.02, sig digs, 0. And they're saying that that constant only works at that temp. So the temperature doesn't really come into play. They're just saying that this reaction's at this temperature, so this is the value we use. Okay, what's going on here? 0.120 moles of hydrogen iodide is placed in a 500 ml flask until equilibrium is reached. So we're starting with just HI. So I am going to set up an ice table to organize my data. Okay, we're starting off with 0.120 moles in a half-liter flask. So that was moles, not concentration, not moles per liter. So now I've got moles per liter, and that's going to work out to be 0.240, capital M for moles per liter. Okay, that's where we're starting, nothing else. So we have no product initially. I stands for initial. Okay, the change that's going to happen, it always moves towards the zeros. So we are going to move this way. So we're going to gain product, gain, and these have a 1 in front of them. So that's gain 1x, gain 1x. This one is going to lose because we're moving away from it. So minus, lose, and we're going to lose 2 amounts because of the coefficient of 2. Lose 2 amounts of HI, gain 1 amount of H2, and gain 1 amount of I2. So to get our equilibrium concentrations, we add the top 2 rows, 0.240 minus 2x, x, x. So those are our 3 equilibrium concentrations. Now, yesterday, you were given one of these 3 values. You were either given the answer to this, or this, or this, and we could solve for x. Today, you're not. So here's why these are a little more complicated. What we can do is use our equilibrium expression to solve for x. So the equilibrium expression is concentration of I2, equilibrium concentration of I2 and H2, 1 of each, divided by the equilibrium concentration of hydrogen iodide squared, and that's really important. Don't forget to square. Okay. Now we can substitute in our values. So the concentration of iodine, switch colors here. Okay, so the equilibrium concentration of iodine is X. The equilibrium concentration of hydrogen is X. Okay, that takes care of those two. The equilibrium concentration of hydrogen iodide is this, 0.240 minus 2x. And this is the step students always forget. Square the bottom and then put the entire denominator in brackets. Phew, so I've taken the equilibrium expression and I've added the actual values for the equilibrium concentrations. But they're x. We still don't have a way of solving for x. But we know this, that the value of this whole thing is equal to 2.00 times 10 to the minus 2. Okay, so here's the big moment. We can graph this and solve for the value of x. Or you can multiply it all out, get a quadratic function, and use the quadratic formula. What would you rather use? I know from experience that the graphing calculator is the way to go. Okay, so we're going to learn how to graph these. Hopefully you already do, but if not, that's fine. So in your graphing calculator, we're going to call this side of the equation y1, and we're going to call this side y2. So we're going to enter these into our graphing calculator and graph it up. So here we go. I think I have a graphing calculator on here. There it is. Okay, so y1. So I'm going to say this out loud because you're not going to be able to see the buttons that I hit on the calculator. So y1 is 2.00. And I went to the y equals button on the top left corner. So y1 is 2.00 second EE for exponent, and the EE is just above the 7. So that's EE, second EE to get exponent, -2. Okay, so there's my y1. Arrow down to y2, which is x squared. So I'm going to hit the x button and the x squared button. So x squared divided by, and I need those double brackets, 0.240 minus 2x, brackets, hit the x squared button, squared, brackets. Okay, so I have entered y1, y2. Now I'm going to hit the graph button on the top right. Graph it. Whoa, okay, I had this set on a different, I'm going to go back to Z standard number 6 and graph. Okay, so if you've got a standard setting on your window, this is what it looks like. Now this is really hard to see the intersect, so we're going to zoom in. So I'm going to hit the zoom button, and I like Z box number 1. It allows me to use the cursors and set the cursor where I want, hit enter, and then stretch out a box. So I'm going across and I'm going down. And the intersects are always going to be really close to 0. So this is the part of the screen I want to zoom in on. I hit enter and it redraws the window. Okay, and there it is. So the blue line is y1. That is my 0.02, or 2 times 10 to the minus 2 for y1. And then the red line is my y2 function, which is kind of crazy. I'm going to zoom in a little more just to show you what this thing actually looks like. So cursor over and up a little bit. Okay, enter, stretch out a box. So we should be able to actually see the intersect here. Enter. Okay, there's y1, the blue line, and there's y2. Okay, this thing has 2 intersects. So there are 2 correct values for x mathematically, but only one of them works chemically. The value, the left intersect will be a negative value, and you can't have a negative amount of chemical, so you can always ignore the negatives. So it's going to be the intersect on the positive side of the graph. So to find the intersect, I am going to go second button, second, and then the trace or calculate, top right, second, calculate, number 5, intersect. Put the cursor close to where the intersect is to show the calculator, and then hit enter 3 times. Enter, enter, enter. And it finds our x intersect, and that is 0.026457. Perfect. Okay. So now that value of x is stored in our calculator as x. So I can clear this, go back to my equilibrium expressions, and my first value was 0.240 minus 2x. So I'm going to put in my calculator 0.240 minus 2 and then hit the x button and it will calculate it. Okay, 0.187. So I'm going back here. I just put this into the calculator, 0.240 minus 2x, because we just solved for x. And the x intersect, I'll just write it down, was 0.0265 ... So that's stored in our calculator as x, which, by the way, is the answer to these 2. So I now know those equilibrium concentrations, and this one I just got from the calculator was 0.188. For simplicity, we're just going to go 3 sig digs on all of our answers. Make our lives a little easier. Okay, so every final equilibrium concentration, 3 sig digs. Okay, so that's how you use an ice table with equilibrium expressions. What do you think? We're going to do 3 more examples, And that's why I said today's lesson is a long one. There's lots of little twists and curveballs we can do with these things to make them a little more challenging. So it's not just blindly repeating the same pattern every time. Okay, let's rock and roll. Round 2. The nice thing about this lesson is, like, a lot of students tend to get lost on this one when I teach it in class. So you get a chance to rewind it, watch it again if you didn't understand an example. Okay, second example. Here we go. I don't know how we're doing for time, but whatever. Just keep rolling along. Okay, so gaseous NaCl decomposes. NaCl decomposes into NO and Cl2. Equilibrium back and forth. Okay, balance it. 2 chlorines, 2 chlorines, 2 NO, 2 NO. Okay, there's our balanced chemical equation. They're giving us the equilibrium constant. It's very small. It's to the -5. That's tiny. Okay, and they're saying 1 mole of NaCl in a 2-liter flask. So that's our initial concentration. 1 mole in a 2-liter flask. Okay, so that works out to be 0.5 moles per liter. And that's it. It's an empty flask other than that. So those are zeros. Okay, at this point, if you think you've got this dialed in, you can go ahead and try and solve this question on your own. Pause your video and then come back and see how you did. If you still want to just follow along with me, that's fine too. Okay, so our change, you always move towards the zeros because you have to turn something that already exists into something that doesn't. So this is going to go forward. So we're going to gain product, gain 2 amounts of that one, and gain 1 amount of that. And we are going to lose 2 amounts. Again, we're using those coefficients to determine the amount of gain and loss. Okay, so at equilibrium, we will have 0.50 minus 2x. 0 plus 2x is 2x. 0 plus 1x is 1x. Okay, there's our 3 equilibrium concentrations. We will use our equilibrium expression to solve for this. Products over reactants, concentration of Cl2, sorry, equilibrium concentration. Equilibrium concentration of NO squared, do not forget that. And equilibrium concentration of NoCl, also squared. Okay, so we substitute into this and we get Cl2 is X, NO is 2X squared. Again, this is one students always forget, is that squared, and then everything is wrong after that point. And this one is 0.50 minus 2x squared, and we'll bracket the entire denominator. Now, some students, here's the other error that they make. They forget the squareds, and some students take a shortcut here and they go, oh, x times 2x squared is 2x cubed. Wrong. 2x squared is the same as 2x times 2x, which is 4x squared, times x is 4x cubed on the top. So you can either put in this part into your calculator. Whoops, I went for blue there. So you can either put all of that into your calculator, or you can put 4x cubed. Just don't put 2x cubed. It's wrong. Okay. So now we're going to graph it. So y1 is 1.6 times 10 to the -5. There's our y1. And then everything that's outlined in gold is y2. All right, let's go put it in the calculator. Y equals, so this first one is 1.6, just got to look it up here, 1.6 times 10 to the -5, 1.6 second exponent -5. Okay, and y2 is 4x cubed. 4x cubed, I need the math button, number 3. 4x cubed divided by double brackets. Where did it go? 0.5 minus 2x squared. 0.50 minus 2x brackets squared. Okay, so just double check it. That looks good. I'm ready to graph it. I hit the graph button, and there is my graph. Now I'm zoomed in from the last window, and that's kind of good, actually. I can see where that intersect is going to be. And I'm just going to zoom in a little more just because. So number 1, Z box. Okay, let's go down a little bit. Make sure I don't miss the intersect across. Enter. And stretch out that one. This is going to have, looks like 2 intersects, one on the positive, one on the negative, but we only need the positive side. Let's see if we can find it there. Holy smokes, that is one crazy intersect. It's hard to even see it there. They overlap. Okay, well, let's calculate the intersect, see if we can find it. Second, calculate. Intersect. Okay, so it's picking there, and that looks reasonable to me. Hit enter 3 times. And we get 0.00609. 0.00609. That doesn't seem right to me. Let me go back and just check my y's. 0.5 minus 2x. Oh my gosh. It's squared twice. I have an error. Get to see me fix my mistake on the fly. I don't know why I got a squared in there twice. Let's delete that one. And graph it again. Uh-oh. Go to. I just have to get rid of that. There we go. Graph it again. Second, calculate, intersect. There we go. 0.00973. See? Even I make mistakes. I make a lot of mistakes. Best way to learn, make a mistake, but don't make it twice. Okay, so now we have our correct value for x stored in there. So I'm going to clear this off. Stored in x. And I'm going to go back to my equilibrium concentrations. And I'm going to plug this one into my calculator first. 0.50 minus 2x. 0.50 minus 2x. Enter. 0.480. Okay, and this is 2 times x for my next one. 2x is 0.0194. 0.0194. And my last one is just x. 0.00973. And these are all concentrations, moles per liter. So there are my 3 equilibrium concentrations. Boom. Got it. Okay, how you doing? 2 down. So those are the basic patterns, and now a curveball. So what makes this one a curveball? This one will be a little trickier. Okay, so they're giving us the equilibrium reaction. Okay, let's organize our data. So here's our equation. What have we got here? Initially, we have 3 moles in a 1 liter flask. So that becomes 3 moles per liter of CO. Oh, I think there was a mistake in your study guide on this one. Now that I look at it, it's supposed to be, yeah, this is a mistake. It's supposed to be 3 moles of, I wrote that in the wrong spot. There's my first mistake on that. So it's 3 moles of CO2 in a 1 liter flask. So 3 moles per liter. I guess there's not a mistake. And this one is 3 moles in a 1 liter flask of H2. Okay, so here's the curveball to this one. We're starting with all product. And if you remember on day 1 or day 2, we had those 3 reactions of iodine where we did 3 different things, and one of them was starting with all product. No reactant. Weird, but possible. So on our change with this one, which way is this thing going to move to reach equilibrium? Well, it has to move towards the zeros, so it's going to go in reverse to reach equilibrium. So we're going to be gaining reactant. Gain 1x, gain 1x, lose 1x, lose 1x. These are all coefficients of 1. So at equilibrium, we have 0 plus 1x, which becomes x. 0 plus 1x becomes x. 3 minus x. 3 minus x. Okay, I'm going to get you to pause the video here. I want you to try and finish this one off on your own. When you graph it, your graph should look like this. And we will ignore the negative intersect and go for the positive intersect. And you should get a value of 0.9207 when you graph it and solve for the x-intersect. So go ahead and try it and then come back and you can see the solution here. Okay, Kc is 5.10, which equals concentration CO2, concentration H2 over CO, concentration H2O. And that is 3.00 minus X times, let's put it in brackets, 3.00 minus X over X times X. If I want to shorten that, 3.00 minus X squared over X squared. Okay. And that whole thing is 5.10. All right, now here's the goofy part when I go to put this in my calculator. Okay, whoops. So y1, 5.10, clear, 5.10. Okay, and y2 was brackets 3.00 minus x squared divided by x squared. I think I'm going to put brackets around that x squared. Back that up. Brackets x squared. Okay, graph it. So here's the goofy part. When you go to graph this, there's nothing on the screen. You're like, oh, what did I do wrong? That's because we were zoomed in really far on that last one. So I'm going to go zoom number 6, Z standard, to reset my window. Oh, there it is. Okay. Now you'll notice the blue line is really high this time. That's because y1 is 5.10. So we're 5.1 units up on the y-axis. And as I said, 2 intersects. We ignore the one on the left and we go with the one on the right. Second, calculate, intersect, put that cursor over towards the positive one and hit enter 3 times. And there it is, 0.9207. Okay, back to our question. X equals 0.9207. That's stored in your calculator. You can now solve for those values and we are good to go. Yay. Okay, hopefully you have no questions on this because I can't really answer them right now. Challenge question. If you're absolutely cooked right now and you're ready to stop and go and start on the assignment, you could. Or if you just want to take a break, get up, walk around, do some push-ups, go outside for a few minutes, come back, and then take a look at this last question. I know we've been going on for a while here. As I said, big lesson today. Okay, so I will work on this one and see you back in a few minutes after you've taken your break. You can watch this and then see what to do for your assignment. Excuse me. Okay, I'm going to go through this one fairly quickly. So setting up our ice table, what do they give us? 4.30 moles. Oh yeah, this one does not say the volume of flask. Same question as above, so it's a 1 liter flask. Oh, let's use 3 sig digs. So these all become capital M mole per liter. 4.30 mole per liter water, 4.30 mole per liter. I guess I should just put concentration here and then I don't have to keep rewriting concentrations. Okay, 4.30, 4.30, 3.50, and there's no carbon monoxide. So it has to move towards the 0. So we're going to gain 1x, gain 1x, lose 1x, lose 1x. Okay, x, 4.3 plus x, 4.30 minus x, 3.50 minus x. Plug them into the equilibrium expression. 5.10 is, and I don't like to do this, but I'm just going to skip the equilibrium expression and go straight to substituting in to save a bit of time. I find when students do that, they forget to square things. This one doesn't have any squares, so I know I'm safe. Over x times 4.30 plus x. End of bracket. So always bracketing the entire denominator. Okay, so graph it, solve for x, and x is 0.475. And you may have to play with the zoom feature to get your window to find that. I'm not sure. I'm not going to put it in the calculator again to save time. You've seen enough of those. Okay, so this is the assignment that is due. I can't remember the due date. You can check in the Google Classroom. Okay, that's the one that's due. So it's the second half. You should have already done numbers 1 to 7 yesterday. And if not, you're going to do those as well for marks. So you're going to hand that in to me. But before you do this, I would go and do some practice ICE questions. There's some in your textbook. Answers are in the back of the text. And there's also this worksheet in your study guide. And I have given you answers in this lesson in the Google Classroom for you to self-check that work. There's no quiz or test this week. It's just this assignment for marks. Okay. All right. I'm afraid to hit the stop button and see how long this lesson was. I know it was a doozy, but I had to get through it. It was a big one and an important one. Make sure you get ICE tables dialed in and equilibrium constants. Okay. Take care, everybody. And I'll see you after the weekend. Oh my gosh, 41 minutes. I knew it was going to be long.